All right, welcome to a discussion of the first part of the section 7.4 WebAssign. So we're looking at partial fraction decomposition. In particular, we're looking at linear factors here, so factors of degree 1. Taking a look at this first guy here, we are in the linear factors section. Note that x squared minus 4 downstairs. When we undergo a partial fraction decomposition, we want to factor the denominator polynomial as much as we possibly can. That x squared minus 4 can cancel to be x plus 2, x minus 2, which is in fact exactly what is shown over here on the right. So taking each of the factors downstairs, x plus 2, x minus 2, and putting an appropriate lesser degree factor above, namely a constant factor above, life is good here. That looks exactly of the form that we desire. What about this next guy here? Here we've got a repeated factor. The factor of x is repeated twice. Now, if you have a factor repeated twice or repeated 3 times, you're going to have 2 or 3 corresponding fractions in your partial fraction decomposition. So the issue with this expression and why this would be false is because the a over x squared, we would actually need an a over x and then a b over x squared before we get to the c over x minus 9. When you have a repeated factor that's repeated twice, you would take that factor in the form of it expressed once and in the form of it expressed twice and set up a separate fraction for each. So this is false for that reason. Right, working through this here, the denominator is unfortunately not factored. That's probably one of the first steps that they'll walk you through whenever we're working through this exercise. If you do factor the denominator, it's going to be 6x plus 1 times x plus 1. Looking at it here, not too wild or crazy to factor. But then once you set up the factors downstairs, ultimately then you're going to set up a decomposition. So you'll have like a over 6x plus 1 plus b over x plus 1, and you'll write a common denominator with your a's and b's. You'll then equate numerators and work to find the a and the b. Once you find the a and the b, you'll have a pair of fractions in sum, each of which will be sort of bite-sized to integrate. Once you integrate them, I guess life will be good in a sense, because then you'll have your capital F function that, because this is a definite integral, you'll later plug in 1 and plug in 0. So if I was doing a definite integral with partial fractions, I'm probably just going to forget about the 0 and 1 initially, set those to the side, just work out the capital F function using the classic partial fraction decomposition sort of steps of expressing the decomposition, finding the a and the b, expressing the decomposition without the a and the b in sort of numerical form, and then integrating each individual fraction within that decomposition. Once I get the capital F, now I'm going to plug in 1, now I'm going to plug in 0 and subtract. That's probably the way I'd go about this. Of course, this is a tutorial exercise, so how they go about it is anybody's guess. What about this one here? Hey, we've got 3 factors in the denominator. We got a y plus 2, and a y minus 3. If we want to use the method of partial fractions, I'm guessing here they just want an a and a b and a c. I'm guessing that's what they want here. Maybe they're looking for the exact numbers. Yeah, I guess using the method of partial fractions. So if they're looking for the exact numbers here, we'll have to, to work this out in general, you wouldn't put an a and a b and a c in this block, but you would sort of write out an a over y plus b over y plus 2 plus c over y plus 3. Make a common denominator with your a's, b's, and c's, and then whatever's in the numerator you equate to whatever's on the left-hand side, and then work to deduce what a, b, and c are, probably by eliminating the coefficients one at a time, like setting y equals 0 will eliminate the a, setting y equals minus 2 will eliminate the b, and setting y equals 3 will eliminate the c. Once you figure out what your numerators have to be, then you've got an expression which integrates very quickly, right? Because whatever this number is up here, you just got ln y times that number. Whatever the number is up here, you've got ln y plus 2 times that number. And whatever the number is up here, you've got ln y minus 3 times that number. After I get the capital F function is probably whenever I'm worrying about the bounds here, plugging in 2 and plugging in 1. The bounds are basically an annoyance, but it gets down to a single number, which I guess WebAssign prefers over a giant algebraic expression. Evaluating this integral, this is a classic partial fraction decomposition. We'll have an a over x minus 1, we'll have a b over x plus 7. We'll take that expression with the a over x minus 1 and the b over x plus 7, and we'll make a common denominator, equate the numerators, and then plug in x equals 1 and x equals minus 7 will eliminate a and b in accordance and solve for what a and b are. Once we know what a and b are, we'll have two bite-sized pieces in sum equal to our original functions expression, which will be much simpler to integrate. That's really the whole idea of partial fraction decomposition, is to take this fractional expression that's not so easy to integrate and to break it into bite-sized pieces. Down below, okay, hey, the denominator's not factored, but that's okay. If you do factor it, you get what, x minus 2, x minus 3. So you'll take this expression with maybe the factored denominator of x minus 2 and x minus 3, and then you'll say, okay, well, that's got to be equal to some a over x minus 2 plus b over x minus 3. With the expression including a and b, you'll make a common denominator. Then you'll equate the numerators and eliminate the a and the b respectively by plugging in 2 and 3. And then once you figure out what your a and b are, you'll have these two fractions in sum, which will integrate nicely. And yeah, once you get your capital F function after integrating those nicely, there's going to be ln's involved here. Then you're just going to plug in 1, plug in 0, and life is good. What about this last example? Okay, so this last example is probably the most sophisticated one because we do have a repeated factor. Note the x minus 1 is squared, which means in our decomposition, there's going to have to be one fraction over x plus 1 and a second fraction over x plus 1 squared. There's going to be a third fraction over x plus 2, and right, we'll just take that sort of one bite at a time. So we'll have a over x plus 1, b over x plus 1 squared, and c over x plus 2, all in sum. Just like in the previous cases, we'll take that expression with the a's, b's, and c's, and we'll make a common denominator. We'll equate the numerator, so the numerator would be equal to x squared plus x plus 1, and then we'll just start plugging in. We can plug in x equals minus 1, plug in x equals minus 2 to eliminate letters as much as possible. Now what will happen when you plug in x minus 1 in this case is that you will eliminate both a and b. Well, it'll allow you to find c, which is great, but then it's like, well, how am I going to find a and b otherwise? Because when I plug in x equals minus 2, I just get an expression with a and b. That's only one equation. Another thing you could do is just plug in x equals 0, let's say. That's easy to evaluate with. I recommend doing x equals 0 for that reason. And then you plug in x equals 0, you'll get an expression with a, b, and c, but you already know what c is. So by replacing what c is, you'll get two equations with a and b, which you can ultimately go back to your Algebra 2 methods to solve that two-equation system. You have two equations with a and b. You can work out the details to figure out what the a, b, and c are. Now, once you get the a, b, and c, integrating the a over x plus 1 and the c over x plus 2 are going to be just like the previous cases. Integrating the b over x plus 1 squared, you'll have to use u sub for, but it's actually not too bad because u is just x plus 1, so du is just dx, and yeah, life is good whenever you integrate that. But ultimately, as always, you take those three bite-sized pieces from your decomposition and utilize those. While this is a definite integral, which is going to require plugging in a 4 and plugging in a 0 and subtracting, my recommendation, as I mentioned before, is just set the bounds aside initially. Go through the decomposition, find your a and b and c. Integrate each of the terms in your decomposition so that you then have your capital F function. Once you've got your capital F function, plug in 4, plug in 0, and subtract. Because we're not using substitution here, there's really no shortcut in this method. We just got to take it sort of one bite at a time. But yeah, that's it. That's the extent of the homework exercises, and hopefully this video can be helpful.